It's almost 3 o'clock. Walter Monk used to always fall asleep at the talk about 3 o'clock in the afternoon. So I'm feeling the same way. So I'm going to talk about a lot of the work we've done in New Zealand, mostly looking at these so-called slow slip events, using pressure gauges to measure the vertical uplift that occurs during one of these slow slip events. Why are we working in New Zealand? First of all, the distance from the trench. Where is this?
The top one. Pointer is the top one.
Top one. There we go. One of the nice things about New Zealand is the distance from the trench to the shoreline is quite short. That means that the GPS sites on land can see these offshore slow slip events that are occurring, which means we know they're happening. Most subduction zones, the trench is so far from the coastline that unless the event is very big, we probably wouldn't even know it's happening. The other thing that's happening is the slow slip events in New Zealand tend to be very large. There's a lot of work on slow slip events in like Cascadia. Those tend to be down dip in the lock region. They tend to be very small. Whereas these slow slip events we're looking at here involve about 20 centimeters of motion on the interface, which corresponds to a fairly large earthquake. A slow slip event can be thought of as an earthquake in very slow motion, happens over maybe 1 to 2 weeks. But we're getting about 20 centimeters of slip over a very large area. It corresponds to something like a high magnitude 6 earthquake. So we talked about this earlier. There was a lovely movie earlier talking about subduction zones. This is sort of a model of New Zealand. Here we have New Zealand here. We have the Pacific plate getting dragged down underneath New Zealand. As it moves underneath New Zealand, it drags the island New Zealand down. So if you have a pressure gauge out here near the trench, you see the pressure gauges being pulled down while the plate continues to move. If you're looking at one of the GPS sites, the GPS sites get dragged to the west between slow slip events. In most subduction zones, the interface is locked from depths of maybe 30 kilometers down to maybe 50 kilometers. I'm making this up, I can't remember. And in most subduction zones, the big earthquakes nucleate at something like a depth of 30 kilometers and propagate downward. One fairly rarely gets an earthquake that breaks into these shallower depths. It's a little unclear why that's true. The general idea was this is sort of soft and gooey and things are just sliding or creeping. But we do have these things called tsunami earthquakes where we get breaking all the way up to the trench. And they're called tsunami earthquakes. They produce big tsunamis. Tuhuku, the earthquake broke all the way to the trench. There's something like 50 meters of motion in a small region near the trench. And it basically produced a very large tsunami. So if we don't have slow slip events, what we expect is basically over long periods of time between the big earthquakes, the depth to gradually increase offshore. And typically there's sort of a uplift near the shoreline. The shoreline typically tends to be sort of a hinge plane. So you can think of over long periods of time, there'll be a bit of shallowing at near the coastline, deeper offshore. And one of the things we're interested in is, can we make pressure measurements over very long periods of time and see this so-called secular change? Because what that would tell you about is where the region's locked down here. Is that transition from upward, from basically hinge lines, tells you something about what part of the interface is locked. And we started off early on talking about one of the big interests in seismologists is understanding which parts of the fault are locked, which parts are creeping. And of course, why do you care? It's because those parts that are locked are the ones that are accumulating the strain that's going to produce the shaking that's going to knock down Seattle. Let's see what else I see. So typically, I think there was that nice movie. Typically at great depth, things tend to be unlocked because it's just simply too warm. You just simply get creeping of the interface. And a lot of the slow slip that's been studied in Cascadia is happening at sort of this boundary below the locks region. In New Zealand, much of the interface seems to be slipping during these slow slip events, almost all the way to the trench. let's see, so. Just to summarize, we're using pressure gauges to measure the vertical motion associated with slow slip events. We care because it tells us something about which patches of the fault are locked and which ones aren't. Let's see. And one of the last reasons we study slow slip is that several of the recent very large earthquakes appear to have been preceded somewhat shortly beforehand by large slow slip events. This work in New Zealand is a whole bunch of different people. It was sort of started by Laura Wallace. It's involved a big Japanese group, New Zealand, and I got dragged in later on. And then Randy Watts has joined us with Matt Way in the most recent project. Let me just do that right here.
I don't know.
It's the clock, I guess. All right, bingo. So here's a basic New Zealand tectonics. We're mostly going to be talking about the North Island. We have the Pacific plate getting pulled down underneath the North Island at about 5 centimeters per year. So over 100 years, you expect to see about 5 meters of motion. And we've got GPS sites on land. This is some of the data from the GPS sites. So we've got particularly down in the south, the GPS sites are moving to the west. It's the Pacific plate subducts underneath. This Chatham Island plateau gives you very strange tectonics. In New Zealand, we have subduction along the North Island on the west side, and along the South Island on the east side, and this strikes the fault down through the middle. You have a great deal of variability in the amount of coupling, with very little coupling to the north and very strongly coupled to the south, which is very nervous for Wellington. All right, so I can just move. All right, I'm just too busy. All right, no, went the wrong way. All right, so this is a map of the coupling. So the blue parts sort of imply zero coupling. And here's one of these GPS records. And so what we see is a GPS site right here. It's Gisborne. And what you see is between these slow slip events, the site's moving westward at roughly 5 centimeters per year, which is the subduction rate. Then you get one of these slow slip events over a period of 2 weeks, it sags back to the east. And over a series of slow slip events about every 1 to 2 years. And if you look at very long time scales, the site ends up back at the same place it started with at 20 years earlier, suggesting essentially all of the strain is being released in these slow slip events. What was unknown when this figure was produced is what the coupling looks like offshore. So red is sort of fully coupled. There's this big transition down in the middle of the North Island. And we'll see one experiment from down in there. And these contours are sort of the accumulated slip inferred for those slow slip events. You see the deep events, which are kind of typical of most subduction zones, and these shallow events had got 40 centimeters over a period of about a decade, showing essentially all the slip, at least up to near the trench, has been released in these slow slip events. All right. So there are a whole series of experiments. We've seen the Hobbits experiment up here. Randy talked a little bit about that. The second experiment was a project that was basically Japan and New Zealand instruments up here, again in the Hobbits area, and then a bunch down in the Hawke's Bay area. And then finally, there's been a really nice experiment that was done by the New Zealand group and the Japanese group down here in this sort of region where there's a transition from sort of fully locked almost to the trench to essentially unlocked further north. All right, next one. All right, so you've seen this picture before, and we remarked, here's the GPS data, here's the pressure data. First thing to remark is just how incredibly poor the signal to noise is on this pressure data estimate of vertical uplift. But we did get at least a map that's somewhat believable about what the extent of the slow slip was out near the trench. Here's that little map of the slip. This is the maximum slip on their face was something like 20 centimeters. These lines up here, the inferred vertical uplift from the pressure gauges. These lines, horizontal lines, are from the GPS data. Combining the two, we get this map of slip on the interface. One of the interesting things is the slip seems to wrap around two of these seamounts that are being subducted. They're essentially now completely buried underneath the wedge of sediment above it. These seamounts, where it seems to be the seamounts are acting like an anchor. They're not, slow slip events are not slipping in those regions. In 1947, there were two earthquakes that are thought to have happened, and they seem to match up with where these two seamounts happened. So maybe long-term, those two patches where the seamounts are being subducted are essentially fairly locked, and that gives you a region which can produce an earthquake and do a lot of damage on shore. What else do I want to say? All right. So this just is sort of renewing, talking about how we got from the original seafloor data, which is up here, to this data that we're showing the uplift associated with the slow slip event. The first thing we had to do is to detrend and de-drift the pressure data. That's the detrended, drifted data. We fit an exponential plus a linear term. This is a really messy thing to have to do. We're now using A-0-A drift-directed instruments in the next experiment, which I think is going to greatly improve our confidence in our results. We took the original data, we picked some reference sites, and at this point, we didn't have Eric Fredrickson's nice paper saying you should use long strike data. So when we deployed the instruments, we put instruments out on the incoming plate where we were sure that the slow slip events weren't going to be there. So we subtract off some of the offshore sites from the sites up on the slope. And this is the result here. We then filter out the tides and we flip it so that it corresponds to vertical uplift or a decrease in pressure. That's how we got there. All right. Where am I now? Oops, I missed the site. All right. We've did another experiment about 2 or 3 years ago. This has been worked out by Katie Woods. This involved Japanese and New Zealand instruments up here off Gisborne and a bunch of Le Mans instruments down here in the Hawke's Bay region. And there were slow slip events both up near Gisborne again and down in the Hawke's Bay region. This is the first time we had deployed some A-0-A instruments. And those turned out to be fairly critical to improving our estimate of the slow slip that occurred down in the southern site. We ended up reducing our estimates of the amount of uplift that occurred, basically because we had better estimates of the drift on the instruments. We also used a oceanographic model to look at very long term and use that to correct the data as well, which seemed to agree with results from A-0-A instruments. And what that did was just we ended up reducing our estimates of the slip. But the sort of numbers for the slow slip were fairly similar, something like 15 centimeters down here and 15 centimeters up here. The sort of scale. This gives you an idea of sort of the scale of these lock patches in the New Zealand area. And what else do I want to say? All right. All right, this is just the maps again. And so we're interested in the relationship of these slow slip patches to previous earthquakes in this region. You know, one of the questions, so if you have slow slip and you're loosening all the strain, should you have earthquakes? Well, it's probably true that there are patches that are slipping these slow slip. They're surrounded by regions that seem to be locked. Perhaps that's where the earthquakes are happening. You still have this general question: can you have slip in these slow slip regions? Are we losing all of the accumulated strain? And here are these two earthquakes up in the Gisborne area in 1947 that did quite a bit of damage that seemed to be associated with those seamounts. And there are something like 7 or 10 subsidence events in this Hawke's Bay region that suggest that there have been a series of earthquakes in that region. All right, and here's the latest experiment that was done by the Japanese and New Zealand groups. And indeed, here's the GPS data from land showing a big event. I think this must be their project there. I wasn't part of this experiment, so I'm sort of going to just sort of give you my impression of what they got. Let's see. One of the interesting things about this area was there's a huge amount of seismicity and so-called tremor. Tremor is sort of a continuous vibration on the interface, and that we see this in Cascadia. That tremor seemed to propagate very slowly, sort of meters per second type numbers. And they have a very nice story about the propagation of the small earthquakes during the and preceding the slow slip event down here. One of the interesting, most fascinating things is a very sharp boundary where there is not seismicity south of this boundary. I think they're trying to understand that. And this is real. There's plenty of instruments down here to see the earthquakes. They're just simply not going down there. That's one of the mysteries that is coming out of some of these observations. So let me talk about technology. The Lamont instruments use this super high resolution, high sampling rate version of the parascientific gauge. By high sampling rate, we're running at 125 hertz. There's a paper describing how this is done. Why are we sampling at these high frequencies? It's not to see the slow slip events. We're using it for seismology. This is what an ocean floor spectrum looks like. This is counting noise of the instrument. Basically, at high frequencies, we can't really get down to seafloor noise level. We're using a DPG. You'd find that the spectrum continues down like this. But with this sorts of data, we can see the body wave arrivals from large earthquakes at high frequency. In this middle band here, we can see so-called surface waves, Rayleigh waves. This is a very typical deep ocean spectrum. This is basically just ocean waves. These are the so-called infragravity waves. They have amplitude like a centimeter. This cutoff is just simply the hydrodynamic filtering as you get to, because ocean waves are exponential, e to the minus kx, kz. So this cutoff is typically around 30 seconds in the deep ocean. As we go into shallow water, this rolls off, and eventually you start to see the effect of ocean waves, the big swell and so on the shelf and so on. And this is a so-called microseismic peak, which is a wave-wave interaction pressure signal. This is an acoustic wave. And this is just a record of an earthquake we took off New Zealand. So here are the two pressure gauges showing the P wave arrival and the S wave arrival. And this is a seismometer that's on the instrument as well. So the really important stuff we've added to the instruments now are these so-called A-0-A drift correction. We have 50 of these instruments out in the current experiment off New Zealand. A-0-A is basically to remove drift from a parascientific gauge. It works because the drift in a parascientific gauge is essentially due to a change in the offset of the gauge, not in the gain of the gauge. So if you measure the drift at low pressure, it turns out to be almost exactly the same as the drift at high pressure. So if you have a way to measure the drift at low pressure, you can correct your long-term records. So what we do is we have a valving system that here we are at 2,000 meters. We suddenly switch the valve so that the pressure gauges measure the pressure inside the pressure vessel. And we also measure the pressure inside the pressure vessel with an accurate barometer. We measure the drift, the relative offset between the pressure gauges and the barometer correct the pressure data. We have two pressure sensors in the instrument. This allows us to check for accuracy. Here's the original record showing the drift over time. The blue curve and the red curve are the two different pressure gauges. We use the A-0-A to correct them, and they drop on top of each other. And they seem to agree with each other to accuracy of better than a centimeter over 1 year. And one of the questions is what the long-term accuracy of A-0-A is. We just know it wandered around less than a centimeter during a year. If we just kept those measurements going, would it stay within a centimeter over 10 years? We just don't know that yet. All right. So the next experiment is also going to have in the same areas of a set of quarks. This is very important to us for seeing very small slow slip events. Again, we're in the Gisborne area here. Quarks, so basically you go out with a drill ship, you drill two very, very expensive holes into the seafloor, you put a pipe into the hole, you cap the top of the pipe, and then you measure the pressure in the pipe and the pressure in the ocean, subtract the two to remove the tides, and that's because scale eddy field. This quark system is a very sensitive detector of slow slip events, because as one of these events propagates along the interface underneath one of the boreholes, it strains the formation above the interface, and you get either compression or dilatation, and that either increases the pressure or decreases the pressure in the borehole. And so here's one of these GPS records on land here, and here's the two boreholes. And what you can see is we see a slow slip event offshore on the GPS, and here's this big signal on the within the borehole, sudden increase in pressure. So there's a borehole there and a borehole here. The other one shows a drip, then an increase. That probably corresponds to where that pulse propagating along the interface is relative to the borehole. We see a whole bunch of other little small things in the GPS that show up quite well on the quark borehole. So that's very exciting. All right. All right, and then the other really important new technology in the next project, Randy talked about this a little bit earlier, so I'm going to it, are these CPIs. And the CPIs are measuring near bottom current. So we're hoping to apply because near bottom current is proportional to the perpendicular horizontal pressure gradient, at least on a flat bottom. They also measure pressure, and there's an inverted echo sounder that gives us an indication of something about the thermocline depth. It's basically the time it takes for the pulse of sound to go up to the surface and back down again. That depends on where the thermocline is, how fast it is. And I won't go into this, Randy talked about it. So here's our latest experiment. Randy talked about it. We have 15 big joint experiment, New Zealand plus Japan plus Randy and myself in that way in the US. We have 52 instruments out with something like 40 pressure gauges, something like 25 seismometers, and of the pressure gauges, 15 have this A-0-A on it. We have 12 CPIs, and we're really interested in what we're going to learn. And we've learned from Eric Frederick's going to have the sites well to the south, well to the north, outside of the main slow slip area region, so we can apply reference corrections to long axis. I'm not going to read this through. It basically repeats what I just said. That's out there.